In this video, we're going to solve the wave equation using Fourier series. We're going to show that the most general solution to the wave equation on an interval is the sum of what are called standing waves. So here's the problem. You take a string, think of it as a guitar string or something, and you pluck it. So it has a certain position at an initial position, and of course the tension in the string tends to pull it back down towards equilibrium. And the restoring force is proportional to how much this string is bending. And that's the second derivative of the function with respect to x. So f of xt is how much this string is bent out of shape at position x and time t, where this is the x-axis. The restoring force is proportional to the second derivative, and since acceleration is force is mass times acceleration, that says the second derivative of f with respect to t is a constant times the second derivative of f with respect to x. This is called the wave equation. Now, you should think of that as being the second derivative of vector is a times f, where our vector is actually a function. It's an element of L2 of the interval. And a is not a matrix, it's c squared times second derivative. And you should think of this as behaving very much like the problem of second derivative of a vector in a finite dimensional space, being a matrix times that vector. And we know how this behaves. You either get coshs and sinches or cosines and sines, depending on whether the eigenvalues of a are positive or negative. Now, in this case, our operator is c squared d squared by dx squared, and we already found the eigenvalues of that in a previous video. The eigenvalues are of the second derivative are minus n squared pi squared over L squared, but our a is c squared times the second derivative, so we get an extra factor of c squared. And that's negative, so we always get oscillations in time. We get sines and cosines, not coshs and sinches. And the sines and cosines go with a frequency which is square root of minus the eigenvalue. So that's n pi c over L. And the eigenvectors are sine waves. So our general solution is going to be a sum of, you multiply the eigenvector times one coefficient times cosine plus another coefficient times sine. This is our most general solution, viewing f as a vector and psi as a vector. If you spell it out as functions of x, you say that f of xt is a sum of, now I put the vector over here on the right, sine of n pi x over L, and the coefficients on the left, an cosine omega nt, bn sine omega nt. And what these are, each of these terms here is a particular sine wave that's oscillating in time. So the basic mode is the lowest eigenvalue. It's sine of pi x over L, and it vibrates with a frequency of pi c over L. So for example, if this was a piano string and we happen to hit an A in the fourth octave, great. That's the main vibration, and it's oscillating at a certain frequency, which is the frequency of the note that we call A. But then there's a certain contribution from this mode, and this mode oscillates at twice that frequency. You see, the nth mode oscillates at a frequency proportional to n. The nth mode has the frequency is going to be n times the very first mode. So twice the frequency. In music, that's an octave. So if this is going on at an A in the fourth octave, this is going on at an A in the fifth octave. The third mode is going on at a frequency 3 times as big as this, and that's 3/2 as big as this, so that's a major fifth above A, so that's an E. The fourth mode, which I didn't draw in, goes at frequency 4 times the base, so that's 2 octaves above A, which is another A. And the fifth mode is going to be a C sharp in the 6th octave, the 7th The sixth mode is going to be E in a sixth octave. The seventh mode is actually pretty ugly. You don't want to hear that. It's not a nice note. The eighth note is going to be an A again. The ninth note is a B. The 10th note is a C sharp. Okay, so we've got our general solution, but we'd like to know what the coefficients A, N, and B are. And this all comes down to initial conditions. So we describe our initial conditions in terms of two functions. The first is the value, how much the string is displaced at time 0. We call that f0. And the other thing we look at is what is the velocity of the string at time 0. And we call that g0. So in general, the function is given by this sine. And if we take its derivative with respect to time, the derivative of cosine is minus sine, and you get a factor of omega. Derivative of sine is cosine, and you get a factor of omega. So the initial shape of the string tells you what is f of x 0, and cosine of 0 is 1, sine of 0 is 0. So that becomes this simpler expression. So the coefficients an are precisely the Fourier modes of f naught. And how do you get the Fourier modes? Well, you integrate. You take 2 over L times the integral of f naught times sine of n pi x over L dx from 0 to L. The derivative of f with respect to time at time 0, its initial velocity, if you will, if you plug in t equals 0 into this second expression, you get cosine is 1, sine is 0, and you get this. So the coefficients Bn are not the Fourier coefficients of g naught, but they're close. Bn is 1 over omega n times the nth Fourier coefficient of g naught. So instead of being this, which is the nth coefficient, you have to divide by omega n. And there's our Bn. So let's do an example. In this example, we're going to assume that the string is originally bent along a parabola, along the curve x equals x squared. And for simplicity, I'm going to take L equals 1 and C equals 1. And that means that our nth frequency is just going to be n pi. It's n pi C over L, but it's C over L is 1. And we're going to take our initial velocity to be a tent function. That is to say, the middle is heading up very fast. The ends aren't heading up at all. Intermediate is heading up by an intermediate amount. So this is the rate at which the string is moving at time 0. This is the shape of the string at time 0. So we compute our Fourier coefficients of this by integrating this function times sine pi x dx. And this was done in chapter 6.9 of my book. In fact, it's on page 185. It's called example 3. I'm not going to work out the gory details of the integral, but the answer comes out to n over n cubed pi cubed if n is odd, and 0 if n is even. And then you take this tent function, and you figure out what its Fourier modes are. Its Fourier coefficients wind up being 4 over n squared pi squared sine of n pi over 2. And that's example 2 on page 184 if you want to look it up. And Bn is 1 over omega n times the Fourier coefficient. So that comes out to 4 over n cubed pi cubed if n is 1 more than a multiple of 4, minus 4 over n cubed pi cubed if n is 3 more than a multiple of 4, and 0 if n is even. So now that we know an and bn, we can write our solution for all time. Our function is the eigenvector. By the way, eigenvectors, when they're functions, when we're working in a space of functions, sometimes you call them an eigenfunction instead of an eigenvector. But it's still a vector in the sense of being in a vector space. Then we have our coefficients times cosine, coefficients times sine. And the even terms have coefficient 0. The odd terms give you this for the cosine, and plus or minus 4 over n cubed pi cubed for the sine. And if you spell it all out, the first term looks like this. The second term is a factor of 27 smaller because it's going as 1 over n cubed. The third term is a factor of 125 smaller than the first term. To a pretty good approximation, it's just going like the very first term. Okay, so what have we learned? We've learned that a general solution can be written as a combination of sine waves that go up and down and up and down and up and down. If you had just one term, you'd have something that would have the same shape all the time and just go up and down and up and down and up and down. And that's called a standing wave because it doesn't go anywhere. It oscillates, but it always looks like sine of n pi x. Now, when you take a combination of standing waves, you get waves that go back and forth and do all sorts of interesting things. But you can always write them as linear combinations of just the plain standing waves.